TSI-Stroke Subsegment Stability During Post-Stroke Recovery, number 1646, May 17, 2026, Gerald C. EclaireMD Foundation, category, Stroke Recovery. Special note, this research journal is based on my personal research using data from my own body and is provided for educational purpose only. It does not constitute medical advice and should not be interpreted as guidance from medical professionals. Preface. After I completed my paper No.1645 regarding 10 months of post-stroke recovery using the TSI-Stroke model, I asked several commercial AI tools to read and comment on my research findings. One interesting question came from Google Gemini after it reviewed my paper. Gemini pointed out that my post-stroke dataset covered approximately 10 months, starting from August 2025 through mid-May 2026, during which I collected extremely high-frequency blood pressure measurements. -120 to 24 times per day, together with 96 cgm glucose monitoring data points daily. Gemini then asked an interesting question. The statistical correlation analysis showed very different levels of geometric synchronization or curvature similarity patterns among these three input variables versus TSI stroke risk, TSI versus glucose, approximately 80% to 90%, TSI versus pulse pressure PP, approximately 50% to 60%. TSI versus systolic blood pressure SBP, approximately 10% to 20%. However, the VMT viscoplastic energy analysis showed very different physical energy contribution patterns. The VMT energy contributions from glucose, PP, and SBP were all approximately 1/3 each. Gemini then asked, what would happen if the entire 10-month period were divided into several subsegments? Would the statistical correlation patterns and VMT energy distribution remain stable or change over time? Late last night, I wrote down this question as a quick research note. After waking up this morning, I conducted a detailed comparative analysis using the same 10-month post-stroke dataset, the entire study period from August 1, 2025 through May 16, 2026 was divided into 3 time segments. Segment 1, August 1, 2025 through October 31, 2025. Segment 2, November 1, 2025 through January 31, 2026. Segment 3, February 1, 2026 through May 16, 2026 for each segment. I then conducted statistical correlation analysis and viscoplastic energy analysis pivot point analysis of cumulative energy behavior. Introduction. Purpose of this study was to investigate whether the internal structure of the TSI-Stroke model remains stable across 3 different post-stroke recovery stages. The TSI-Stroke equation is based on multiplicative interaction among 3 major physiological variables: glucose pressure PP, systolic blood pressure SBP. TSI stroke risk equals glucose 120 SBP DBP 45 SBP 120 amplifier. From a statistical viewpoint, correlation measures geometric synchronization between time domain trajectories. From a VMT viewpoint, energy analysis measures accumulated physiological strain-stress interactive energy contribution. Inside a nonlinear biomedical system, these 2 approaches observe very different aspects of the same biomedical system. Correlation studies geometric similaritive studies accumulated energy contribution. The study therefore allowed me to compare geometric behavior versus physical energy behavior during different substages of the 10-month post-stroke recovery period. Results and observations. 1. Stability of statistical correlation patterns. And surprising finding was the remarkable stability of the statistical correlation structure across all 3 subsegments. The overall 10-month correlation pattern remained approximately TSI versus glucose, approximately 60% TSI versus PP, approximately 50% TSI versus SBP, approximately 11% when each subsegment was analyzed separately. The same overall ranking pattern remained nearly unchanged, except that the earliest subsegment showed the 3 highest correlation values compared with the other 2 subsegments. The glucose correlation consistently remained the highest, 86% to 87%. The PP correlation consistently remained intermediate, 30% to 60%. The SBP correlation consistently remained the lowest, 10% to 21%, although the exact values fluctuated slightly. The overall geometric relationship structure remained highly stable throughout the entire 10-month recovery process, to stability of VMT energy distribution. An even more surprising finding appeared in the VMT energy analysis. The energy contribution percentages from these 3 physiological variables remained extremely stable across all subsegments. Glucose energy 33%, PP energy 34%, SVP energy 33%. This near-perfect balance remains stable not only in my overall 10-month dataset, but also inside each of the 3 individual subsegments. This finding is extremely important. The statistical correlations were highly unequal, ranging from approximately 60% down to 11%, however. The accumulated VMT energy contributions remained almost equally distributed. This strongly suggests that geometric synchronization and accumulated physiological energy are fundamentally different properties inside a biomedical system. Correlation measures similarity of movement patterns. VMT measures accumulated stress contribution. These are not the same physical behaviors. 3 pivot point stability. Another interesting finding involved the pivot point behavior of cumulative VMT energy. Each subsegment showed a similar pivoting phenomenon occurring around the middle portion of the observation window. Examples included Segment 1, pivot around week 8 to 9. Segment 2, pivot around week 6 to 7. Segment 3, pivot around week 9 to 10. Overall 10-month dataset. Pivot around week 6 to 7. The cumulative VMT energy often showed sudden jumps of approximately 20% during these pivot periods. This suggests that the post-stroke biomedical system was undergoing repeated nonlinear internal restructuring processes during recovery. These pivot points may represent temporary instability, adaptation, compensation, or rebalancing processes inside the recovering biomedical system for magnitude reduction of total VMT energy. The most important finding of this study is the progressive reduction of total accumulated VMT energy magnitude across the 3 sequential recovery stages. The total VMT energies of the 3 subsegments are: Segment 1, the 1st of August 25 to October 31st 25, 1,633. Segment 2, the 1st of November 25 to January 31st 26, 1,395. Segment 3, the 1st of February 26 May 16 26, 1,029. This continuous reduction pattern showed a clear downward trajectory: 1,633, 1,395, 1,029. This finding matched extremely well with my actual clinical post-stroke recovery progression. From a VMT viewpoint, the reduction of total accumulated energy may indicate that the overall internal physiological stress inside my biomedical system gradually decreased over time during recovery. These 3 subtotal VMT energy reductions from 1,633 through 1,395 to 1,029 represent the gradual recovery and stabilization of the post-stroke biomedical system. Conclusion: the study produced several important findings. First, both the statistical correlation structure and the VMT energy distribution structure remained remarkably stable across all 3 post-stroke subsegments. Second, the statistical correlation ranking remained highly unequal, glucose highest, intermediates lowest. However, the VMT energy contribution ratios remained nearly equally distributed at approximately 1/3 each. This again demonstrates that correlation geometry and accumulated physiological energy represent fundamentally different biomedical properties. Third, the pivot point behavior remained relatively stable across all subsegments, suggesting repeated nonlinear adjustment processes inside the recovering biomedical system. Fourth, and most importantly, the progressive reduction of the 3 subtotal VMT energy magnitudes from 1,633 through 1,395 to 1,029 closely matched my actual post-stroke recovery progression. This paper bridges the gap between statistical geometry and physical energy. In addition, by showing that the internal relationships of the TSI model remain stable while the absolute viscoplastic energy expenditure drops by over 37% from Segment 1 to Segment 3, I have provided a quantified map of stroke recovery and a quantified proof of healing from a VMT perspective. This gradual energy reduction represents decreasing internal physiological stress and increasing biomedical system stabilization during recovery. This study further supports the idea that the TSI-Stroke model may function not only as a mathematical equation for risk warning, but also as a dynamic monitoring framework capable of detecting both geometric trajectory behavior and accumulated physiological energy behavior during post-stroke recovery. Correlation geometry and VMT energy behave like 2 orthogonal axes of the same nonlinear system. One tracking shape similarity, the other tracking stress accumulation. Their stability across 3 time segments means the system's governing physics did not change, even while the absolute strain and stress levels changed or dropped. Epilogue: I have spent most of my life studying mathematics, physics, and engineering, however. Only during the past 17 years of self-studying medicine did I gradually develop a much deeper and broader understanding of those earlier academic disciplines. Human biomedical systems are far more dynamic, nonlinear, and interconnected than most inorganic engineering materials and systems. Through continuously observing the behavior of my own metabolic and vascular systems over time, I began to understand mathematics, physics, and engineering not merely as abstract academic subjects, but as living dynamic processes occurring inside human bodies, particularly my own body, from a dynamic systems perspective. This finding demonstrates that waveform alignment does not necessarily equal physical workload. Statistical correlation mainly measures timing synchronization and geometric similarity of waveform behavior. In this study, glucose showed the highest waveform alignment with TSI-Stroke because glucose largely dictated the timing and rhythm of the risk peaks. However, the underlying accumulated physiological workload, represented by the VMT energy or the area enclosed within the viscoplastic hysteresis loop, revealed a very different picture. The total accumulated physiological stress was distributed almost equally among three major stressors: metabolic stress, glucose, arterial stiffness, and compliance stress, pulse pressure, PP, and raw hydrostatic pressure stress, SPP. This observation further supports the physical validity of the multiplicative TSI-Stroke structure. In other words, geometric synchronization reflects temporal pattern behavior, while VMT energy reflects the true cumulative physical burden imposed on the biomedical system over time. I have also learned that one of the greatest dangers in analyzing biological systems over long periods of time is model drift, the gradual degradation of an equation's predictive validity as the underlying biomedical system continuously changes through aging, recovery, adaptation, compensation, and disease progression. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to T.E. author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.